Picture this. A comet older than our Sun, racing through our solar system at over 150,000 miles per hour, passing so close to Jupiter that it could theoretically be captured by the giant planet's massive gravitational pull. But astronomers have just revealed why that's not going to happen, and the physics behind it is absolutely mind-blowing. On July 1st, 2025, the Atlas telescope system in Chile spotted something extraordinary. A tiny speck moving against the backdrop of stars, traveling at an impossible speed. Within hours, astronomers around the world realized they were witnessing something truly rare. The third interstellar object ever discovered passing through our solar system. They named it 3I/Atlas, and this cosmic wanderer has been captivating scientists ever since. Here's what makes this story so fascinating. 3I Atlas didn't form anywhere near here. While everything else in our solar system, every planet, every moon, every asteroid, shares a common origin from the same cosmic cloud that birthed our Sun 4.6 billion years ago, this comet is a complete outsider. Scientists estimate it's been traveling through the cold darkness of interstellar space for approximately 7 billion years. Think about that for a moment. This object is older than our entire solar system. It was already ancient when Earth was just beginning to form. The comet has been putting on quite a show as it makes its way through our neighborhood. Multiple NASA spacecraft have captured images of it, including the Hubble Space Telescope, the James Webb Space Telescope, and even the Europa Clipper mission currently journeying toward Jupiter. What they've seen is remarkable. A reddish-colored nucleus somewhere between 1,500 and 3,500 feet in diameter, surrounded by a glowing cloud of gas and dust called a coma, with a brilliant tail streaming behind it. But the really interesting part is happening right now. 3I Atlas is heading straight toward Jupiter, and on March 16, 2026, it's going to pass remarkably close to the gas giant. And when I say close, I'm talking about 33.3 million miles. Now that might sound like a huge distance, but in cosmic terms that's incredibly tight. To put it in perspective, that's only about 1/3 the distance between Earth and the Sun. Here's where things get really technical and absolutely fascinating. Jupiter has what scientists call a Hill sphere. This is the region around the planet where Jupiter's gravity is stronger than the Sun's gravitational pull. Think of it like Jupiter's gravitational territory. Anything that enters this zone slowly enough could potentially be captured and become a new moon of Jupiter. The size of Jupiter's Hill sphere varies depending on where Jupiter is in its orbit, but on March 16th, when 3I Atlas makes its closest approach, Jupiter's Hill sphere will have a radius of about 53.5 million kilometers. Now get this. Astronomers have calculated that 3I Atlas will pass at a distance of 53.6 million kilometers from Jupiter. That's an almost perfect match with the edge of Jupiter's Hill sphere. The difference is only about 60,000 kilometers, which sounds like a lot, but on this scale it's remarkably precise. It's like throwing a dart from New York and landing it within a few inches of a target in Los Angeles. Some scientists, including Harvard astrophysicist Avi Loeb, have pointed out how statistically unusual this precision is, though the scientific community remains divided on what, if anything, this coincidence means. But here's the crucial question. If 3I Atlas is passing so close to the exact zone where Jupiter could capture it, why won't it become Jupiter's 96th moon? The answer comes down to one simple but powerful factor: speed. When 3I Atlas reaches Jupiter, it will be traveling at approximately 66 kilometers per second relative to the giant planet. That's about 147,000 miles per hour. This is absolutely critical, because in order for Jupiter to capture an object and make it a moon, that object needs to be moving slowly enough that Jupiter's gravity can hold onto it. At the distance where 3I Atlas will pass, the escape velocity from Jupiter is only about 2.2 kilometers per second. Think about it this way. Imagine you're trying to catch a baseball. If someone tosses it to you gently, you can grab it. But if someone fires it at you from a cannon at 200 miles per hour, it's going to sail right past you, no matter how good your reflexes are. That's essentially what's happening here. 3I Atlas is moving so fast that even though it's entering Jupiter's sphere of gravitational influence, the planet simply can't slow it down enough to capture it. The math is actually quite elegant. 3I Atlas would need to somehow lose nearly 64 kilometers per second of velocity, slowing down from 66 kilometers per second to less than 2.2 kilometers per second in order to be captured. That's 97% of its speed. There's simply no natural mechanism that could cause such a dramatic slowdown. Comets do experience small changes in velocity due to outgassing as their ice is vaporized near the Sun, but these effects are tiny, measured in fractions of a kilometer per second, not tens of kilometers per second. Scientists have been tracking these small velocity changes in 3I Atlas very carefully. Observations show non-gravitational acceleration peaked at about 89 times 10 to the negative 9th astronomical units per day, squared around perihelion, its closest approach to the Sun. While this sounds impressive, it's actually quite modest and typical for an active comet. These small accelerations have caused the comet's trajectory to shift slightly compared to what pure gravitational calculations would predict, but nowhere near enough to allow Jupiter to capture it. What makes this encounter even more interesting is the timing. The comet will pass close to one of Jupiter's small irregular moons called Euphemy just one day after its closest approach to Jupiter. Euphemy is a tiny satellite, only about 2 kilometers across, part of a family of moons called the Ananke group. These are thought to be fragments of a larger object that was captured by Jupiter long ago and broke apart. The fact that 3I Atlas will pass within about 30 million kilometers of Euphemy has sparked discussions about whether we might witness any interesting gravitational interactions, though at these distances, and with 3I Atlas's high speed, any effects would be minimal. Some researchers have theorized, mostly as thought experiments, about what would need to happen for 3I Atlas to leave behind any material in orbit around Jupiter. The calculations show that any fragment would need to receive a precisely aimed velocity kick of exactly the right magnitude and direction, cancelling out that 66 kilometer per second relative motion. For a natural breakup to produce such a kick is essentially impossible. The gravitational binding energy of a comet simply isn't strong enough to accelerate fragments to such high speeds. The trajectory of 3I Atlas is what astronomers call hyperbolic, meaning it's not bound to our solar system. It came from interstellar space, it's making one pass through our neighborhood, and then it's heading back out into the void, never to return. When it was first discovered, it was traveling at about 137,000 miles per hour. As it fell toward the Sun, gravity accelerated it to about 153,000 miles per hour at perihelion, its closest approach to our star on October 29, 2025. Now it's heading back out, gradually slowing as the Sun's gravity pulls on it, but it will eventually reach the same speed it had when it entered, and escape back into interstellar space. Jupiter will give it a slight gravitational nudge as it passes, bending its path slightly, but not nearly enough to trap it. The planet's immense gravity, which has shaped our solar system in countless ways, capturing dozens of moons and protecting the inner planets from countless asteroid impacts over billions of years, simply cannot overcome the comet's tremendous velocity. NASA's Juno spacecraft, currently orbiting Jupiter, might be able to observe the encounter if mission planners decide to redirect some of its instruments toward 3I Atlas. Some scientists have calculated that with careful maneuvering, Juno could potentially get a closer look at the interstellar visitor, though this would require using precious fuel reserves. The European Space Agency's JUICE mission, also heading toward Jupiter, has already captured images of 3I Atlas and may provide additional data. What happens after March 16th? 3I Atlas will continue its journey outward, passing beyond Jupiter's orbit and eventually leaving our solar system altogether. Decades from now, it will cross through the outer reaches of the Oort cloud, that vast sphere of icy bodies surrounding our Sun. And then it will be gone, returning to the darkness between the stars. This encounter reminds us of just how special planetary capture events really are. Jupiter didn't accumulate its 95 known moons by catching random objects flying past at interstellar speeds. Most of its large, regular moons probably formed from the same disk of material that created Jupiter itself, billions of years ago. The irregular moons, like Eupheme, were likely captured, but these captures would have occurred when the objects were moving much more slowly relative to Jupiter, possibly during the early chaotic period of our solar system's formation, when there was more debris around and more opportunities for gravitational interactions to slow objects down. So while 3I Atlas will indeed pass through Jupiter's hill sphere and give us an unprecedented opportunity to study an interstellar object's interaction with a giant planet's gravitational field, it's moving far too fast to be captured. Physics has spoken, and the numbers are clear. Jupiter's gravity, as powerful as it is, simply cannot overcome that incredible velocity. But don't feel disappointed. What we're witnessing is still extraordinary. 3I Atlas is only the third confirmed interstellar object ever detected passing through our solar system. Each one gives us a precious glimpse into the nature of objects that formed around other stars, carrying information about planetary systems beyond our own. The fact that we can track it so precisely, predict its path months in advance, and coordinate observations from multiple spacecraft and telescopes around the world, and even in deep space, shows just how far our understanding of celestial mechanics has come. As 3I Atlas makes its closest approach to Jupiter in just a couple of months, astronomers will be watching carefully, gathering every bit of data they can. They'll study how the comet's jets behave in Jupiter's powerful magnetic field, whether the encounter triggers any changes in its activity, and precisely how its path is deflected by the giant planet's gravity. Every measurement adds another piece to our understanding of these mysterious visitors from beyond our solar system.